Okay, I know this looks like the end of the world, but let's get into it a little bit at a time. This, I promise, is not quite as bad as it looks. It's bad, but not as bad as it looks. Our original function is f of x. It's the solid line here, so I'm going to highlight that one blue. The original function looks, it could be a cubic, it could be a shifted sinusoid maybe, but it's got that kind of behavior, up, then back down, then back up. Now, these other two curves describe its first derivative and its second derivative, and so really the information that they're giving us is stuff that we could have figured out anyway. The first derivative is this line, and what does it mean? Here, the first derivative is high and positive, which means our slope is high and positive, which means the line is going uphill fairly fast. Yep, there it is. As this line drops, it's still positive, but it's not as big anymore, this section. What does that say? The slope is dropping. The slope is positive but dropping. That means this line is rising, but not as fast. Slower, slower, slower. What's going to happen here? The function is flat, and sure enough, the derivative hits zero right there, meaning the slope just hit zero. So this derivative is telling you what you can see on the graph anyway. At this point, the line flattens out. Then the derivative goes negative and it gets bigger. What does this mean? Downhill a little bit, downhill a little more, downhill a lot, as in dropping fast. And sure enough, that's exactly what the curve's doing. It drops faster and faster. Then it starts to turn back, dropping fast, dropping slow, dropping very slow. That's reflected by the derivative going big and negative, medium and negative, small and negative. So how far this line is from zero tells you how fast you're dropping. The fact that it's negative tells you that you're dropping and not rising. Here, the derivative hits zero. What does that mean? Function's flat. When the derivative is zero, your slope is zero, so that means the line's flattened out. And now, as this line rises, slow, faster, fastest, the derivative goes low, medium, high, and positive. This means rising slow, rising faster, rising real fast. So everything that the derivative is telling us, we could already see from the graph. If we didn't have that red line, we could still see this is rising fast, rising slow, flat, dropping slow, dropping fast, dropping slow, flat, rising slow, rising fast. What does the second derivative say? Well, the second derivative is our concavity. It tells us if we're curving up like a happy face or curving down like a sad face. And if we track that one, this is even simpler because there's fewer changes in it. Down here, the second derivative is negative, and it's fairly big, which means our line is curving downward fairly quickly. That's this curve here. Curving downward more slowly. So here, in this part, the line is almost straight. It's got some downward curvature, but it's certainly hard to see. That represents this section where we have concave down curvature, but not very much of it. When the second derivative hits zero, what does that mean? Inflection point. It's a coincidence that these lines are crossing at the inflection point, but still, this line is inflecting because it's going from concave down to concave up. And as it becomes concave up, the second derivative goes positive. And as it rises, this is saying the upward curvature is gentle, sharper, very sharp. And on the line here, we have gentle curve up, a little more curve up, very sharp curve up here. If you were driving along this section, you'd have your wheel cranked way over to the left. So the blue curve is the main one, and the other ones are just describing or emphasizing features of it that we kind of could have figured out anyway. All right, so now that we have all that, let's see if we can blaze through these questions. On the interval a to 0, meaning the left half, f of x is positive, right? This function's always above 0. I'm just going to put pause to save space. And f prime of x f double of x, the second derivative, is consistently negative, which would mean the function's concave down. Between 0 and d, so the right half, the function is negative, the blue line is neg, and the f double, the second derivative, the green line, is positive. Not too bad so far. On the intervals a to b and c to d, so this section and this section, the far left and the far right, f of x is, well, they can't be talking about positive and negative because on AB the function is positive, but on CD the function is negative. That can't be it. Look at this though. They ask about f prime, and on A to D the first derivative is positive. On C to D it's also positive, so we can do that. And if the first derivative is positive, that would mean this function is increasing. I believe that's what they're after. And you know what? Now that I think about it, if this one about the first derivative, they bring up that the function's increasing, I think what they may be talking about here when they said if the second derivative is positive, I think they may have been wanting us to say that the function was concave up. So both of those things are true, and I'm honestly not sure which one they wanted. So there they both are. On the interval b to c, so this middle section, the function is, well, the function is the blue part, decreasing, I believe it would be, because the first derivative is negative all through there. I think that's what they want, decreasing. And the first derivative is negative, which is saying the same thing, that our slope is negative. At 0, right here, f of x has well, f of x has an intercept, an x-intercept, or actually it's an x and a y-intercept, so I'm just going to say intercept. And I think what they're looking for here is inflection point, but I would say the function has an inflection point. I wouldn't really say the second derivative has an inflection point, but I kind of object to the, if that's what they wanted, I kind of object to the way that they're phrasing it, but the function has an intercept there, and also it inflects there. It goes from concave down to concave up. At point B, right here, f of x has a, what's this called? It's the top of a hill. We call that a local maximum. And the first derivative has a 0, a root. You could call it an intercept, but we don't usually use that phrase for a derivative. We'd say it has a 0 there. And at point C, f of x has a, what's this? It's the bottom of a valley. That's a local minimum. And f prime, again, has a 0. So, as you've seen as I worked through this, there were a number of places where there's more than one way to describe what's happening to a function. You can talk about an inflection point or an x-intercept, and they can happen at the same time. So for some of these, it isn't 100% clear what phrase they wanted, and I tried to give you a perspective on a bunch of the different things that you could say. So if you check solutions or check someone else's work and find you aren't in perfect agreement with these, you may both be right.